Time dilation sounds like science fiction, but it's a hard, tested reality that comes straight out of the work of Albert Einstein. And once you actually understand it, your whole idea of time being constant completely falls apart. The core idea is simple but brutal to accept. Time is not universal. It does not tick at the same rate everywhere. How fast time moves depends on two things: your speed and the strength of gravity around you. This comes from two major frameworks: special relativity and general relativity. Special relativity deals with motion, and it says that the faster you move through space, the slower you move through time relative to someone who is stationary. But don't dumb this down. This only becomes noticeable when you approach the speed of light, which is about 299,792 kilometers per second. At everyday speeds, the effect is so tiny it's basically irrelevant, which is why your brain has never noticed it. But push toward extreme speeds, and the difference becomes massive. To understand this properly, imagine you're inside a spaceship traveling at 90% of the speed of light. Inside the ship, everything feels normal: your heartbeat, your thoughts, even a ticking clock. But for someone watching you from Earth, your clock is running slower. This isn't an illusion or a trick of measurement. Time itself is literally passing more slowly for you. If you somehow reach 99.9% of the speed of light, the effect becomes extreme. While a few years pass for you, decades or even centuries could pass on Earth. This is where the famous twin paradox comes in. One twin stays on Earth, while the other travels at near light speed and comes back. The traveling twin is physically younger. That's not theory. It's a logical consequence of relativity, and versions of this have been experimentally confirmed using high-speed particles and precise clocks on aircraft. Now shift to gravity, which is where general relativity comes in. Gravity is not just a force pulling objects together, it's actually the bending of space-time caused by mass. The more massive an object is, the more it warps space-time, and that directly affects time. The stronger the gravity, the slower time passes. This is called gravitational time dilation. On Earth, this effect is tiny but measurable. For example, clocks at higher altitudes, where gravity is slightly weaker, tick faster than clocks at sea level. Scientists have tested this with atomic clocks placed at different heights and confirmed it with insane precision. But near extreme objects like neutron stars or black holes, this effect becomes dramatic. Close to a black hole, time slows down so much that from an outside observer's perspective, it looks like you're almost frozen in time as you approach the event horizon. A good way to visualize this is to think of space-time like a stretched rubber sheet. Place a heavy ball in the center, and the sheet bends. Smaller objects rolling nearby get pulled in, not because of a direct force, but because of the curve. Time behaves similarly. It slows down in the deeper parts of that curve. So near a massive object, time literally runs slower compared to regions with weaker gravity. This isn't optional. It's built into the structure of the universe. Now here's where people usually underestimate the seriousness of this concept. Time dilation isn't just some abstract physics idea. It directly affects real-world technology. GPS satellites orbiting Earth experience both types of time dilation. Because they are moving fast relative to the Earth, their clocks slow down slightly, special relativity. But because they are farther from Earth's gravity, their clocks also run faster, general relativity. The net effect is a difference of about 38 microseconds per day. That sounds tiny, but if engineers ignored it, GPS systems would accumulate errors of several kilometers within a day. So every time you use navigation on your phone, you're literally relying on corrections based on time dilation.